Here's the practice video for the problems that I have online for you in our lessons and PDF files. And I'm gonna post a link to the video that you should be watching before this one, and maybe you should be watching after you watch this one as well. So when you have, this one is on mirrors. So when you have an object, and you see here object is in red, then there are different rays leaving in all different directions from the object. They're reflected from the object, and when they're reflected, so they will go in all directions, right, from the light that is falling on the object. And we're going to look at 4 main rays that you should be using when you do the diagram for the rays. So in this case, you see the blue ray, the principal ray, the second ray is the focal ray, goes through the focal point, and the third ray goes through the center and comes back through the center. So the one that is principal ray, the first one, it goes parallel to the central line and then through the focal point. The one that is green one, this center ray, it hits the center line at the center and then reflects at the same angle with the center. So you have this angle is exactly the same as that angle that's reflected. So incident angle, this is incident angle, is equal to the reflected angle. So that is another ray. Then you have the focal ray, the one that is in red, number 2, that goes through the focal point and then parallel. So one goes parallel through the focal point, 2 goes through the focal point parallel, and the third one goes through the center and then comes back, reflects again back through the center. So these are the rays that we're going to be looking every single time, but you have to think that there's many different rays that go in different directions, and they also reflect from the mirror, but we only look at these 4 or 3 of, I'm going to choose 3 of them all the time, because 2 of them will give you an answer, but if the third one doesn't match the rule and doesn't come to the same point, so like this point right here, you see right there, there's a point, then you cannot create an image and be sure that that is an image. So you should have two rays always, but third one to check yourself. So let's look at some examples. In the previous video that you should watch before you watch this one, with the example solved by me, I showed you every single example where you place an object, and it depends how your image is going to be located, or where your image is going to be located. So in the first one, so I'm going to call this one the first one. So in the first case, I have the parallel ray in blue through the focal point, through the focal point green one parallel to the center line, and one through the center and back. So when I have an object placed far away from the center of rotation, or the radius of rotation, so point C is where the radius is located, or the center of the circle is located, you're gonna get a real and inverted image. So it is inverted, it's not upright like the object, it's inverted, and it is smaller. So for the second case, so I'm gonna call this one the second case. For the second case, you have an object standing exactly at the center of rotation, where the radius is, the length of the radius from the of the center of the circle or curvature. Then again, I'm going to do the blue ray parallel through the focal point. The purple one is toward the center point, away from the center point, where the center line hits the mirror, the purple one. And then the green one goes through the focal point and parallel. Do you see I have 3 different rays? These 3 different rays show me where my image is going to be located. So my image is located right here. And again, my image is inverted and real. And you could do also the same for the previous case. You could do toward the center and away through the center. It would show you that it's still located in the same position. So you can always check that you found your image in the right spot by checking it, by choosing another third ray out of the 4 ones that I showed you at the beginning. And so it goes for every single one case of these ones. So depending on what kind of case we're going to have, we're going to be talking about it. The only imaginary image you get is the last one. So this one is the imaginary image because it's upright, and it is located somewhere where the rays don't actually meet. So let's look at examples now. So here's the first example. Concave spherical mirror has a focal length of 10 centimeters. So I'm going to write the focal length is given. That is 10 centimeters. Locate the image of the pencil that is placed upright 30 centimeters from the mirror. So the image of the pencil, so the pencil distance to the object is 30 centimeters, so that's 0.3 meters. Find the magnification of the image and draw a ray diagram to confirm your answer. So I need to do the ray diagram. I'm going to start with the ray diagram always first. And so here is my mirror. It's a concave mirror. And I'm gonna use this line as where my points are gonna be. So if that is, I'm gonna choose this to be my center point, or you can call it O, and halfway through is the focal point, and the focal point is 10 centimeters. So the object was placed 30 centimeters away. So here is 30 centimeters away, 3 times the focal point. And then I have my rays. So the first one is parallel through the focal point. Then I have a different one through the focal point, parallel. And then I can check one more ray. I'm going to choose it in orange. Toward the center and back. And also, if I wanted to, I'm not sure if I'm going to be exact the right position or not, but you could go through the center and then it would come back to the center. So you see that your image is located at this position. So when you have your image, when you find your image location, then you can use the mirror formula. So the formula says is 1 over F is equal to 1 over DO plus 1 over DI. DO is the distance to the object and DI is the distance to the image. So I have 1 over 0.1 is equal to 1 over 0.3 plus 1 over DI. Then I get I'm gonna subtract 0.3 from both sides. Actually, I'm gonna divide times every single one of them by 1 over 10. So I'm gonna times every single one of them by 1 over 10. So that will give me, so there's 1 term, 2 terms, 3 terms, every single one of them times by 1 over 10, and I get 1 over 1 equals to 1 over 3 plus 1 over 10 DI. I'm going to subtract 1/3 from 1 over 1, so that gives me 2/3 is equal to 1 over 10 DI. So that's DI. Then your DI is equal to 20 DI is equal to 3, or DI is equal to 3 over 20. So DI is equal to 0.15 meters, or 15 centimeters. The image is inverted, and the image is where the rays actually meet, so it is a real image. So I'm going to write it is real, inverted. And my magnification is going to be negative because it is inverted, and it is di over do, and di is 0.15, and do is 0.3. So that gives me 1/2 or negative 0.5. I forgot about negative. So the size of it is actually 1/2 of the size of the actual object. So that would be your solution for number 1. Let's look at number 2. They say when an object is placed 30 centimeters in front of a concave mirror, a real image is formed 60 centimeters from the mirror surface. Find the focal length. So I have, actually we can start right away with the formula because this one is easy, we just did similar. So we can say 1 over f is equal to 1 over di plus 1 over do. So 1 over f is equal to, your di is 30 centimeters, so that's 0.3. And your image is formed 60 centimeters, that's 0.6. I can skip writing 0.6 and 0.3 if I want to. I just will have my answer in centimeters, so I can write 30 and 60 if I want to. I could write 30 and 60. I just have to remember my answer is in centimeters. So the common denominator is 60. So I'm going to times them all by 60, every single term. So I have 1 term, 2 terms, 3 terms. If I times them all by 60, I have 60 over f is equal to 2 plus 1. So you have 60 over f is equal to 3 over 1, which is just 3. I'm going to flip both sides. So I have f over 60 is equal to 1/3 times both sides by 60. So your focal length is 20 centimeters. And they don't ask you to draw the diagram, so you just found the focal length and you can stop here. And because we did just very similar question with number 1, I'm just going to skip the diagram because it's the same case. When your object is located, oh actually no, let's do this. Let's draw it because the object is located between the center point and okay, so here is my mirror. And if this is the focal point, this would be my center. So this is the focal point, this is the center, and so let's do it like this because we will need 60. So I have focal is 20, so O is 40, this is 60. So if my object is located 30 centimeters away, so 30 centimeters is going to be, so this is 20 centimeters, this is 40 centimeters, this is 60 centimeters. So my object is at 30 centimeters right there because it's a different case for the concave mirror, so I want to do this. So you have parallel through the focal point, then we have through the focal point, parallel, and I'm a little bit off already, so let me fix it a little bit. So here I fixed it. So you have parallel, the blue one, through the focal point, green one to the mirror through the focal point, and then parallel, and then the purple one to the center of the center line and at the same angle of reflection. So, and you see that the object is going to be at 60 centimeters. And this is how difficult it is to do this without graphing paper. You should have graphing paper. Maybe for the next problem, I'm going to insert the graphing paper so it's going to be easier for you and for me to see this. But you see, like if I have wanted to do my green one, I could say this is through my focal point or that one is through my focal point, and it will not come back to the same point. So when you're on a P exam, make sure that you have a graphing paper or the ruler. So the ruler would be a must. for this type of question, because they don't give you the graphing paper. You have to have the ruler. And before we move to the next question, I want to calculate for you the magnification. You saw from the diagram that it was much larger than the object. So the magnification, it was inverted, so it's negative. And DI is 60 and DO is 30. So it looks like it's going to be twice as big as the object and inverted for the negative sign. So here is the next question. A square object is placed 15 centimeters in front of a concave mirror with a focal length of 25 centimeters. So I'm going to write the height of an object is given, and that is 15 centimeters from concave mirror with the focal length. The focal length is given, so the focal length is 25 centimeters. And again, I can plug in my numbers in centimeters, as long as I remember that my answer is going to be in centimeters as well. A round object is placed, there's another one. A round object is placed, let me do a different color. A round object is placed, 45 centimeters in front of the same mirror. So the focal length is given. Okay, another object is placed, and distance to the object is 45 centimeters. My apology, it is the DO from the first object, that is 15 centimeters. Okay, so here it is. DO of the first object is 15 centimeters. Distance to the second object is 45 centimeters. Find the image distance, magnification, and type of an image formed for each object. Draw a ray diagram for each object to confirm your answer. So let's draw our object. So one is, the focal length is 25 centimeters. So let's go back for a second. And the one is placed 45 centimeters. So actually no, I'm gonna do it right here. So I have this, and I'm gonna have this line here. When you have graph paper, then you should do it exact. So we have this much, so I'm gonna do it this long, and then I'm gonna connect this mirror like this. Then I'm gonna say this is the focal length, so this is the focal length. Twice as much is the center, or the radius is twice the focal length. Then one object is placed 15 centimeters. So the first object is placed 15 centimeters, so it's closer than the focal length. And the second object is placed 45 centimeters, which is farther away than the center. And then I have to graph it now. So for the first one, I have toward the center through the focal, or if I do to the center and back, so I can go to the center and back. So I have this, so that goes there and back, so it doesn't change the direction. And I could do another one, let me do it in yellow, toward the center and reflect back. So it's somewhere right here. Do you see that they don't meet anywhere? So it looks like in this case, I am gonna have an imaginary image where the rays don't actually meet. So my image is gonna be formed when there is nothing. There is no rays that are there. So for the first image, we have 1 over the focal length. It's gonna be 25. equals to 1 over the dO, which is 15, and plus 1 over di. Then I can times every single one of them by 75, the common denominator. So I get 75 over 25, which is 3, equals to 75 over 15 is 5, plus 1 over di. And I times this one by 75 as well. Then di is equal to 75 divided by the negative 2, which is 37.5 centimeters. I have to remember my answer is in centimeters. So I got my di. If I need to find magnification, in the image is virtual, so because it meets where there is no more rays meet. And if I need to find my magnification, then we have magnification is gonna be positive, and it is this one, okay, hi over ho, and equals to negative di over do. And because our image is upright, it's going to be positive, so this negative, and I forgot the negative here, and that negative will cancel. So I have di, which is 37.5, to do, which is 15. So that gives me magnification is equal to 2.5 times larger than the original image. So that was for A. And then we did the diagram. So let's do for the second one, when your distance is equal to 45 centimeters. So here I have the mirror again. So for the next one, I have 45 centimeters in front of the mirror. So the focal length is 25, then the center is at 50. So that means my object is right here somewhere. My array diagram. So the first one is going to be parallel to the center line through the focal point, then through the focal point, and parallel. So it looks like my image is going to appear somewhere right here. And this one is real. It is inverted and where the rays meet. And I can always check one more. I could go through the center like this, and it would come, so anything goes through the center does not change the direction. And you can go one more ray. I'm going to do it in light gray, so I could go this ray, and it would reflect somewhere there. So anyways, here is my image. So let's do the calculations now. So here is the image, and here is the object. And here are our calculations. So for calculations, we have 1 over f, the mirror equation, 1 over do plus 1 over di. So your focal length is 25. My answer is going to stay in centimeters. The distance is 45, and I'm looking at the distance of 1 over di. 1 over di. So I could times them all by 225, which is the common denominator, 225. So I'm going to times them all by 225. How do I find the common denominator? Let me show you this quickly. You know this, but I'm just going to show anyway. So 25 is having 5 times 5, and 45 has 5 times 9. I'm going to copy everything that they have in common. So they have in common 5, and then what's left after this. So 5 and 9. So, and that's 25 times 9 gives me 225. So that's my common denominator. And now if I times every single one of them, so this one by 225, this one by 225, and this one. So 225 divided by 25 is 9, equals to 225 divided by 45 is 5, and 225 divided by di. So di is equal to 225 divided by 4, which gives you 56 centimeters. actually 56.25, so it's exact 56.25 centimeters. And then I already said it is inverted, it is real, because this is where the arrays meet. And for the magnification, I have negative di over do, so I get negative 56.25 divided by do, which is 45, and looks like your magnification is going to be equal to negative 1.2, and it's negative because it is inverted.